Astronomy. The first thing I want to point out to you is astronomy might be the most ancient science in human history. We have always been interested in looking up at the cosmos. Both during the daytime, we've been interested in how the sun works to know how to plant crops and when to plant crops, but also and more especially at night. So I'll ask, how many of you have at least once stared up at the stars at nighttime and just gone on a bit of a dreaming wonderment binge? Stars are cool. If you're going to sit back there, I need you to be quiet, okay? We have the Bighorn Medicine Wheel in Wyoming in the US. This has features that line up with certain astronomical events, and that is thousands and thousands of years old. Stonehenge in Great Britain lines up with certain astronomical events. And that's only two. Kaylin, if you're bored, do a dive, type in YouTube, go into Google and do a search for ancient observatories or ancient astronomy, and you'll find many cultures have built monuments to what's up there and what's out there. Stephen Hawking, the famous physicist who passed away a few years ago, said, "We are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe, and that makes us something very special." Some definitions. Now you're going to have to write some stuff down. So in the notes that I gave you, people who study objects in space, well, we call those people astronomers, not astrologers. Did I spell that wrong? Astronomers. There's an O there, Mr. Duick. Astronomers. Almost means star namers. Okay. Another term that we're going to use is celestial objects or celestial bodies. A general term, so objects or bodies, that's a general term for everything in outer space. Planets, moons, stars, asteroids, comets, Dyson spheres if they exist, wormholes if they exist, black holes which do exist. Okay. Radiation is energy transmitted in the form of waves, usually electromagnetic waves on the electromagnetic spectrum. Radiation is typically how we see what's out there, whether it's light, visible light, or other types of radiation that we can detect as well. And the last one we're going to talk about is a spectroscope. You might have done a little bit of spectroscopy in Science 8. We have some spectroscopes somewhere. I couldn't find them. I have a cardboard one here that you can look at later on, and we'll talk about what a spectroscope does. It's one of our primary ways of figuring out what stars are made of. Ariel, we just started. Give me a few more minutes and then we'll go. Okay? So, astronomers, you probably knew that word. Celestial objects or celestial bodies, you probably would have figured out what it meant from the context. Radiation, we've kind of talked about. Spectroscopes, that's probably a new word. Let's talk about the expanding universe. The universe is expanding. It's getting bigger in all directions. How do we know? Edwin Hubble. Where do you folks know the term or the name Hubble from? What object is there out there that's named after Edwin Hubble? No one knows. Pardon me? Watch the show with that name? Okay. So if you've heard of the Hubble Space Telescope, I'm wearing a shirt with a picture from the Hubble Space Telescope. It was our first space telescope, and we named it after Edwin Hubble. Why? Well, here's some of the things that he did. So he was an astronomer at the Mount Wilson Observatory in California. In the 1910s, it was thought that the entire universe consisted of nothing but the Milky, that's too small for you to read, Milky Way galaxy. So up until the 1920s, it was thought that there was a galaxy and that was the universe. In 1924, Hubble showed that faint spiral nebulae, nebula is a cloud of gas and dust, the plural is nebulae, visible in his telescope were much too distant to be in the Milky Way. In effect, he proved that other galaxies exist. He basically opened up the universe. Yeah. No, it's been like, okay, can you move to the front? Yeah. Okay. So let me pause for a second here. Oh, you walked into that one, kiddo. In 1929, so just less than 100 years ago, 91 years ago, he measured the distance from the Earth to several very distant galaxies, and he noticed that they were moving. They were moving away from the Earth and away from each other. That was a shock. At the time, we thought the universe was, here's your fancy word, static, unchanging. It just was there. And he said, wait a minute, I'm finding that stuff is moving out there and moving at tremendous speeds. If you can measure how fast something is going, good morning, my joy. We'll pause for a second. How fast something is going and see where it is, you can figure out where it used to be. You may have done that if you've seen a jet passing high overhead. You can say, well, it must have come from over there if it's heading that way. Got the argument? Is that okay, Eduardo? Okay. So Hubble said, well, look, if I can see which way they're moving, I can go backwards and see where they were coming from. And he noticed that they were coming from, well, let's keep going. When he looked at where the galaxies used to be, they all used to be in the same place at the same time. This aerial was the first evidence for the Big Bang Theory, not the TV show, the actual theory that the TV show was named after. So, what's the Big Bang Theory? If you want me to summarize it in one sentence, the universe expanded from an initial state of extremely high density and extremely high temperature. Everything in the universe was once in a very tiny area and stunningly, staggeringly, fantastically hot. Coming back to the front? Good for you. You made a wise choice. I know. Okay. So that was our first evidence. Hey, if stuff is moving apart, I think it probably, if I go backwards, must have been coming from the same area. I'm not going to go into all the details of the Big Bang Theory. You can do a 4-year PhD just in that. You can find some lovely graphics online. Kaylin, here's one. I don't think I put it in your notes, but basically it says this. Our universe is about 13.7 billion years old. Maybe 13.8, plus or minus a little bit. It started in a very, very small package right there. I'll be with you in just a second. You need to take this diagram, though, and make it expand out like a sphere in all directions. It's just tough to do that on a flat piece of paper. But Lots of stuff was going on at the beginning. We have something called the Dark Ages. After about 400 million years, that's when the first stars formed. And ever since then, the universe has been expanding and cooling off. That's the Big Bang. Question, Ariel? Can you mask up and hustle back, please? Okay. Put your pencils down. Watch the screen. So, one of the most important pieces of evidence for the Big Bang is what we call cosmological redshift, or just redshift for short. So, visible light is wrong color, Mr. Duke. Very small part of the electromagnetic spectrum. And I'll show you that in the next slide. Visible light is a very small part of the electromagnetic spectrum of radiation. And here's the key idea. Red light has a longer wavelength than blue light. If an object, like a star or a galaxy, is moving towards us, its light waves will be slightly compressed in the same way that when a car is moving towards you, you hear the horn at a higher pitch. We would see the light slightly shifted to the blue range. If a star or a galaxy is moving away from us, we'll see the light waves stretched out. They will be, fancy word, redshifted. So here's a slide, not in your notes, of the electromagnetic spectrum, and you can see as waves get stretched out, they get redder. As waves get compressed, they get bluer. And so this is how we can tell whether a star or a galaxy, because we can't go there and see, this is how we can tell whether a star or a galaxy is moving towards us or away from us. Back to your notes. As space expands, yeah. What's the color of it? I'm going to get to that in just a second, because I got to tell you specifically what kind of light we're looking at. It's really cool. It has to do with spectroscopes. So as space expands, the light sent towards us from distant galaxies gets stretched, making it look redder. Now, this isn't something that you can see with just your naked eye, but we can absolutely detect this with instruments. Good day, my friend. So basically, although this is an exaggeration, if a star or a planet or a galaxy is moving away from us, the light that bounces off of it tends to be stretched towards the red. If a star or a planet or a galaxy is moving towards us, it would be blue shifted. We use a technique, here's your answers, Mesa, called spectroscopy to determine what elements are inside stars. We can tell what stars are made of, even though they're very far away, using an instrument called a spectroscope. Spectro and then scopy. Once you've filled in those two words, put your pencils down. Isn't it like when stars turn blue, we'll look at the life cycle of stars in another lesson. We'll see how you can tell which ones are likely to turn into black holes, which ones are likely to go supernova, and we can predict that pretty accurately. It all depends on how much gas makes them up originally. So it depends on what their initial mass is. We'll talk about that. So here is the spectra from a spectroscope of hydrogen. This is the emission spectrum, but typically what we're interested in astronomy is the absorption spectrum. So if you were looking at a star and you saw this pattern of black lines, you would know that that star had some hydrogen in it. And you look at it later on if you want to, you can look through the spectroscope. There's a little opening right here. For example, if I look at the LED ceiling lights over here, I can see a pattern of black lines. If I had a chart with me, I could tell you what elements are making up those LEDs. Okay? So this is for you to look at later on. So that's step one. We have this thing called the spectroscope. Astronomers, back to your notes, are very, very interested in the absorption spectrum. Light that hits the Earth from distant stars on our telescopes has black absorption lines when you run it through a spectroscope. And Ariel, can you put your phone a little further away now? Thank you, my dear. Yeah. I'll try and go a little slower, but we can always get the stuff that you missed if we need to, right? In fact, if you want to, Raphael, if you find it easier just to watch and then get the notes later, you can do that too if you want. So these lines tell us what atomic elements that light has passed through. This is how we know what stars are made of. This is how we know what galaxies are made of, even though we haven't been there ourselves. So if we take the idea of absorption spectrum and we take the idea of redshift, we're almost ready to reach Edwin Hubble's conclusion. So here is the key idea, the key evidence for the Big Bang Theory. When we look at stars, when we look at galaxies, when we look at almost... Folks, need you with me? Okay? I know. But this is the key idea. So this is when I say key idea, we probably want to focus. Here we go. Almost all of the absorption lines from almost all of the stars and galaxies that we observe are redshifted. Thunder should go off on the horizon. Lightning should flash in the distance. This overturned our understanding of the universe. So I couldn't give you a color diagram, but I think on your diagram, the black lines have appeared okay. So here would be an absorption spectrum for an element that wasn't moving. If we look at it through a telescope and we see the same pattern of lines, but we notice it's been shifted towards the blue spectrum, we would say this is moving toward us. The spectral lines, the black lines, have the same pattern, but it's just shifted to the blue end. If we notice that same pattern of black lines, one line, too close together, one line, but we notice that it's been shifted over to the red area, that means it's moving away from us. It's been shifted to the red end. And Edwin Hubble found when he kept looking at galaxies and when he kept looking at stars, almost all of them were shifted to the red end. The universe is redshifted. What does that mean? Everything is moving away from us. What's the explanation for that? The universe is expanding. Okay. So big piece of evidence number one for the Big Bang, redshift. Does that make sense? Is that okay? Sorry, I couldn't get a color picture to photocopy for you, but you can see the lines at least. Okay. So here's a specific example. Here is the spectrum for hydrogen. So hydrogen has two black lines in purple, one single line in blue, another single line in light blue, and a red line in the middle, one line in the middle of red. Red shifted would be moving over a little bit. Blue shifted would be moving there. So the middle image is of a star that's moving away from us. It's been red shifted. The bottom image is from a star or galaxy that's moving towards us. It's blue shifted. Not only that, by measuring the amount of shift, we can figure out how fast the star or galaxy is traveling. I'm not going to show you how to do that, but it's actually a fairly easy calculation. So not only do we know the direction, I can tell you how fast. And if I know how fast, I can work my way backwards to figure out how long it must have taken if we all started in the same area. And lo and behold, I've got the approximate age of the universe. Put your pencils down.
Looks great.
Okay. So other evidence for the Big Bang is what we call cosmic background radiation, sometimes called cosmic microwave background radiation. I think so. I think I forgot to put the blanks in here, but I think there's blanks in your notes. This is radiation left over from the Big Bang expansion. And you can see it in the static on your television, that white, snowy pattern that you get. So, put your pencils down, watch the screen. So, in 1963, two astronomers, Arno Penzias and Robert Wilson, used a radio telescope. So a radio telescope is a telescope, but instead of looking for visible light, it's just looking for radio light, radio waves, to detect cosmic background microwave radiation. That got them a Nobel Prize in physics in 1978.
What's your IP to do it?
We'll come back to that, but got to finish the lesson.
Okay.
This is not in your notes. We have several experiments right now running at the South Pole to study the cosmic background radiation. So we have one called BICEP, the background imaging of cosmic extragalactic polarization. The European Space Agency has launched the Planck space probe to measure cosmic radiation. It ran from 2009 to 2013, so two experiments are BICEP and Planck. I got a video for you in a second, but Arthur C. Clarke says, sometimes I think we're alone in the universe. Sometimes I think we're not. In either case, the idea is quite staggering. So, what do scientists actually believe happened? Pause.